Hey, people. How was your weekend? Make sure I can see everybody. All right, let's see. Today we're going to do section 2.3, interpretations of the derivative. All right, I did grade all of your tests. There's one person that still hasn't taken the test, so I can't review it with you yet, but I will eventually do that, and probably, I assume, next class. The person who hasn't taken it is not here today. I was hoping to talk to him about that. No, he's not here. Just going to take roll real quick. I'll just take a picture of the screen. Okay. So, any questions for me? All right. Okay, so it says so far we've used the notation f with that little line. That's called prime. F prime to stand for the derivative of a function called f. An alternative notation for derivatives was introduced by the German mathematician Gottfried Wilhelm Leibniz when calculus was first being developed. And there's some pluses and there's some minuses to the Leibniz notation. For this class, I honestly think it's a little bit of both. It's good for you guys to learn Leibniz notation because it will help you to determine units of measure in your final answers, which is what a lot of times, and when you get to the applied calculus stuff, students have trouble with, like, what's the unit of measure or whatever. So hopefully we're going to cover that right now and use this new Leibniz notation to help you figure out what units of measure is. Okay. So we know that f prime of x is approximated by, and this, we did this last class, the average rate of change over a small interval, right? Real small changes in x. Like, remember we did like going from x is 1 to x is 1.01, right? So that's what they're talking about, very small changes in x. So for small changes in x, we have the derivative, right? We have the derivative, and remember, that's just the same thing as slope, right? Change in y over change in x. Oops, let me make that legible. And of course, this is just the derivative. And just so we have it in words, this is the slope at a specific point. That is tangent to the curve, or whatever. When I say curve, I mean whatever the graph of the actual function is. Okay, so we're going to go from f prime to Leibniz notation. So we could say a couple of different things. So we can call the derivative of a function f prime. We know that. Another way we could use is we could use f prime of x, also means the derivative of x. In Leibniz notation, you can say dy over dx. And all of these mean the same thing. But like it says here, Leibniz notation, dy over dx is meant to remind us that really derivative is just slope, right? Change in y values over change in x values. So we could say difference in y values over the difference in x values. But where this really helps us out, oh, and I want to add one other thing. You can also, sometimes some books will have d over dx, which means the same thing as like f prime. And then they'll do it like this. All of these are the same thing of saying the derivative of the original function f. And in words, we can say this is the derivative of y in terms, no, sorry, with respect. They like that better. With respect to x. So again, Leibniz notation, what it helps you to do is get the units of measure correctly. And if one thing is in terms of something else, something is a function of something else, it helps you keep the units of measure straight. Everybody with me? Okay. I don't see anybody writing, so I think we can go on. Okay, so we're going to practice writing Leibniz notation for the derivative of the given function. So we want the notation for the derivative of the function that they give us. So what we're going to do first is we're going to start with what is the original function? I did give myself a little more room. I was looking over the notes. I was like, oh yeah, I wanted to do that differently this year. So you guys are going to have to squeeze it in. You don't have as much room as I do. So the original function is d is equal to f of t. So let's put some words to this. This is distance is equal to, or let's say is a function of time. So what goes in the parentheses is the independent variable, right? What it's a function of. Okay, so if we're writing this in regular old, we could say f prime of t is equal to, now we're going to do, let's see, original function derivative. So f of t, and then if we do it in terms of Leibniz notation, we're going to say it's d over the function d over dt. And notice where I get the big function d, or the big letter, the big capital letter D is the distance, right? And we know that distance is a function of time, right? So the big D goes on top because that's our main function, right? Now, this helps you keep track of unit of measure because this big D, as they say here, is in feet. And this is in minutes. But when you talk about the unit of measure for a derivative, it's always feet per minute. Okay, so let's say unit of measure over here. So unit of measure would be feet per minute. And we'll do some other examples that will illustrate that also. So, for example, why don't I just put it right here so that you can connect the two things. I was going to do it later, and I will later too, but I want you to see it here because I was looking through some of the Wiley questions and thinking I better connect it right here. Okay, so let's say I say that I give you this. I say f prime of 7 is equal to -4. And the question is, give it to you what are the units? What are the units of 7? Well, the units of 7 is going to be t, right? Time. So this would be t in minutes, right? So the units of 7 would be minutes. And here's where it gets a little tricky. If I asked you what are the units of -4, you must say feet per minute. And if you think about it, derivative is speed, right? Derivative is slope. So derivative is speed. So you know how you give speed like miles per hour. It would make sense that you give the derivative as a per or rate, right? So you don't want to say that the units of -4 are just minutes because T stands for minutes, right? So if you give, if I'm asking you for the units of the derivative, which f prime of 7 is the derivative at 7, so -4 is the derivative, you want to give it in a rate, unit of measure. Okay, let's try another one. We've got cost of a steak in dollars is a function of the weight of the steak in pounds. So we can say the cost, oops, I don't want that pen. We can say that the cost, oops, oh, that's the wrong pen, sorry, I want this pen. All right, so we've got cost is a function of weight. So if we want, wait, I wanted to say this is, I'm gonna bring this home because this is where last year people had some trouble. This is the original function. So cost is equal to a function of weight. Cost is a function of weight. So now if we want to write the derivative, that would be f prime of w, right? In Leibniz notation, it would be d over dw. And since this is a cost function, that's going on top. So the unit of measure for cost is dollars. The unit of measure for weight is pounds. The derivative's unit of measure, I should say this up here, is what? You guys tell me. It's not a trick question, I promise. I'm not trying to.
Dollars per pound.
Yeah, definitely. It's just dollars per pound. And that's how the fraction sort of helps you out, right? So derivative unit of measure is dollars per pound. Okay, so let's ask the same question here. Let's see. Let's say that f prime of, let's see, pounds, let's say 4 pounds, is equal to I don't know, 12. So, well, actually, let me give you a slightly different example. I'm kind of making this up as I go. Okay, so let's say f of, okay, so instead, let's say we say f of x. No, let's say f of 3 is equal to 12. What are the units of 3? What do you guys think? What are the units of that number 3?
Pounds?
Yeah, definitely. And then what about units of the 12? Now this isn't a derivative, so it is not a rate. So the units of 12 is just going to be dollars, not dollars per pound, right? Just dollars. Because it's not a rate. Remember, slope, derivative, that's all speed, right? So that's a rate, unit of measure, but not if they're giving you the regular function. Now here, you could say, if I had f prime of 2 equals, I don't know, let's say 5. And I ask you, what are units of 2? What would you say?
Pounds?
Yeah, definitely. And then if I say units of 5, you would say what?
Dollars
Yeah, you would say dollars what?
per pound.
Yes, very good. Okay, so I think I made that a little more clear. Any questions on that? So the main thing is when you're talking about the derivative, it's a rate. So your unit of measure means to be something per something, okay? Not just one name. Okay, so anybody want to tell me what they think the original function is here? What's it being? So n is a function of d. N is a function of d. So n is a function of d. And then to write the derivative in Leibniz notation, right, in regular prime notation, we could just say f prime of d, right? But in Leibniz, we would say what? So, all right, so I'm needing, let me do some. So we're going to have d over dd, and d is just meaning derivative, right? And then the n goes on top. And those little lowercase d's are always lowercase d's. So we're talking makes sense derivative. Okay, and then what about the derivative unit of measure?
gallons per miles.
Yes, thank you. So up here, N is in terms of gallons, right? And D is in terms of miles. But if I'm asking you for the unit of measure for the derivative, you're going to give it to me in a something per something, or a rate. All right, well, with this one showing, let's try this one. An employee's pay in dollars is a function of the number of hours worked. So what comes first?
P equals
P.
F of H.
Equals F of H.
E equals F of H, yeah. And the derivative would look like what? Oops, it should be F. In Lebanese notation would look like what?
Lowercase p, lowercase d times f over lowercase d times h.
H. Is H is capital, yeah. So what goes at the top with that?
The p.
Yeah, good. All right, now let's look at, this is in, oops, I keep using that wrong pen. The top is in dollars, right? And the bottom is in hours. So the derivative unit of measure, oops, I don't have, is going to be dollars per hour, right? Okay, and then here they talk about the disadvantage of the Lebanese notation is that it is kind of awkward to specify the value at which the derivative is evaluated. For example, if you wanted to say f prime of 2, that means find the derivative at 2. To do that same thing using Lebanese, you would do this. It's kind of cumbersome. So if you just wanted to find the derivative at 2 using prime notation, you could just say that, right? Well, with Lebanese, you would have to write dy over dx, and then this little line means such that x is equal to 2. So it's a lot more writing. But it does have its advantages because it does help you with units of measure. So you won't always have to use Lebanese. You just know it, and it'll help you answer some questions.
Professor,
Yes.
your voice keeps on fading away sometimes. I don't know if you could do anything about it, but I was just letting you know.
Okay. I think because when I talk, I look at my screen over here. Let me see if I can adjust my screen. Maybe if I do this, then my voice will project that way. Thank you, Felipe. And also, I need to speak with you after class, right? Yeah, we need to set something up is all. You're not in trouble. I hope you're feeling better. Okay, so yeah, so it's not the best thing, but it does have its uses. Okay, so using units to interpret the derivative. All right, so this is a very common example that calc books like to use. It says, suppose a body moves along a straight line and it has this function. It's basically saying, like, suppose there's this function, right? There's this thing or something. They're saying a body. It could be like a microbyte, cell. It could be somebody driving from one place to another, whatever. But they basically mean when they use suppose something moves along a straight line or whatever. They're just saying suppose something happens, right? And we've got some action going on. And they say If you have some function S that is a function of t, let's say time, for example, gives the position in meters of this thing, this body, whatever, from a fixed point on the line as a function of time in sections. So really they're just saying, here's some function of something moving. Okay, so don't get too hung up on the words body, but they do use it a lot. So they're just trying to say something's happening, something is related to something else in some way. So this is Leibniz notation, right? Let me spell his name right. Leibniz. Leibniz. And remember that this can also be written as d over dt, with this being the function itself, right? So what this is saying is that the derivative at 2 is equal to 10. So what this means is when t is 2, we're talking about speed, right? Then you can say that the body or this thing or whatever, the body moves at a speed, and in this class we call it velocity, of 10 meters per second. And notice I'm using a rate, right? Meters per second. Now here's the important stuff. So we know that derivative is speed, right? So if you put 2 in, right, that's time. What is it, seconds? Yeah, if 2 seconds, at point 2, after 2 seconds of being on this travel, he's going 10 meters per second. That's the speed that he's going. Now this is where the relationship comes into what we're about to do. So you can say that because the derivative, right, which we can write as ds over dt, we know that the derivative at 2 is equal to 10. Then what we can say is that the change in s over the change in t, which is the same thing as the derivative, right, equals 10. Now, if you solve this for the change in s, is going to be equal to, because we're just going to take change in t and multiply it by both sides of the equation, is going to be equal to 10 times the change in t. So what this means, and this is pretty integral to the whole derivative idea, okay? What this means is it tells us how fast s is changing for every, unit change of t. How fast s is changing for every unit change in t. So for example, if f was at 2 seconds, it would be 10, right? And if it went to the next unit, f prime of 3, right, then it's going to change by another 10. So it would be 20 at that point. So every unit change. So at 2 seconds, it's this rate, right? But it's changing at that is the actual rate that it will change for every unit. So if it was seconds 3, then it would change to 20, right? Because it changes by 10 for every unit change. And let me do a very specific example for you so you understand what I mean. Put this guy down. Okay, so example 2, the time for a chemical reaction. Hey, Felipe, is my voice better? Is it better since I switched my screen?
Yeah, that's good. That's good. Yeah, it's better.
I put I have 2 screens, one to see your faces and one to write on, and I just put it instead of to the side like this, I put it this way. So I'm glad we solved that. Thank you for saying something. Okay, so example 2, the time for a chemical reaction T in minutes is a function of the amount of catalyst present, A, in milliliters. So what we have is the original function is T is equal to F of A, or in other words, the chemical reaction T is a function of the catalyst present A, and A is in milliliters. So first question, if F of 5 is equal to 18, they're talking about if you put 5 into this original equation and you get 18 out. And notice they're not telling you what the equation is. They're just telling you basically an ordered pair, right? If you put X in, you get 18 out. So what are the units of 5? And then what are the units of 18? And what does this statement tell us about the reaction? Well, let's go to a function here. We've got T equals F of A, where we know that T is in minutes. And A is in milliliters. If we've got an example that says that F of 5 is equal to 18, then same thing, right? If they're asking me what are the units of 5, they're going to be the same as they are in the original minutes. And what are the units of 18? This is going to be in, oh, I got that backwards, sorry. Oops. Erase this. So this is like, I'm going to write it right under. This is T and this is F of A, right? And they'll switch the order on you like that. So the A is in milliliters, right? And the T is in minutes. Okay, so the question is, what does it tell you? What can you guys tell me? What does that tell you? What's going on? No? Well, it's just saying that when 5 milliliters is present, right? Present, the reaction will take 18 minutes. Everybody else set? All right. I'm gonna actually move this up. Okay, so now we're talking about the derivative. If f prime of 5 is -3, what are the units of 5? So the units of the thing that it's a function of stays the same. So this 5 is still going to be milliliters, right? Because it's really the A value. Actually, I should use green. So this is milliliters. And notice this is a derivative. So they're saying the derivative at 5 is equal to, so -3 is the derivative, right? So for that, you're going to use a rate this time. So you're going to say this is minutes per what?
Minutes per reaction.
Nope, what's the other unit of measure? We have minutes and we have what else?
Milliliter.
Yeah.
Milliliter.
Yeah, minutes per milliliter. So in Lebanese, by the way, this would be dt over dA. And remember, this is how fast T changes per unit A. So what does this mean? It means that if the catalyst increases by 1 unit, let's say from 5, or let's say, yeah, from 5 to 6 by 1 unit, then the reaction will decrease by how much? Let me write that down, you guys think about it. The catalyst increases by 1 unit, or actually I should say if the catalyst increases by 1 unit, the reaction, remember, which is time, right? The reaction time will decrease by what? What's the rate here?
-3.
Yeah, very good. So it's going to decrease. That takes care of the negative by 3 minutes. So whenever you're dealing with a derivative, it's telling you that if you have a change by 1 unit, how it's going to change the speed, right? So it's going to decrease by 3 minutes for every 1 unit difference. Let's do one more and then we have a few more. Okay. So let's say I have an economist is interested in how the price of a certain item affects its sales. At price P, a quantity Q of the item is sold. So the quantity sold is a function of price. So if I say, this is the original function, if I say in the original function, if you put 150 in, you get 2,000 out, right? So that means when what? When the price is blank, blank items are sold. What do you think? When the price is what? So if you put something in, something else comes out. So your
When
input
the
is,
price is 150.
yeah, so when the price is 150, you're going to make 2,000 items. All right, and I want to bring this up because I need a little more room for this one. Okay, this next statement, it might be, this is like prime notation. And if you write it in Lebanese, so it would be dq over dp. Okay. And then you'd write this like, okay, you want T. No, we'd want P to be 150. And then write it legibly. So when the price is 150, something happens at negative 25, right? So what this means is that if the price increases, and let's fill in the blank here too. If the price increases by 1 unit, in this case, $1, then what happens? You just did the derivative, what happens? Oops. Items sold will do what? Well, are they going to increase or decrease?
Decrease?
Yeah, right. So the items sold will decrease by how many?
25.
25.
Oh, good. It also tells you that if you put 150 into the derivative, you're going to get negative 25 out. But in words, it tells you that if you increase by 1 unit, then the item sold will decrease by $25. So for example, if we went from 150 to 151, then the amount sold is going to decrease by 25. So it'd be 25 less than whatever it was before. All right. Here's another example. The time and hours that a drug stays in a person's system is a function of the quantity administered. So L is a function of Q. L is in hours, Q is in milligrams. Interpret the statement F of 10 equals 6. What do you guys think? So Q would be the 10, right? And so let's do it like this. F of Q equals L. So basically this is saying when Q is 10, L is 6, right? So let's make that more language friendly. When Q is 10, L is 6. Well, what is Q, right? Q is the quantity, right? So when the dose is 10, right? The dose or the quantity administered is 10, then L is 6. Well, what's L? L is time in hours, right? That a drug stays in a person's system. So you could say that when the dose is 10, the drug lasts 6 hours. It is in hours, right? Yeah. Any questions on that? Does that make sense for everybody? Okay. So you can start with something like this and then just fill in the numbers. Or even if you're doing your Wiley, if you start with something like this, and I think most of those programs are like pull down menus where you say what it means and it gives you several options. Write this down first. It'll be so much easier for you to pick which option. Okay, now we're going to write the derivative in Leibniz notation. So first I'll write it in time. So if you've got f of 10, that's going to give you 0.5. So this is milligrams, and this is a rate. So this is going to be hours per milligram. Okay, so if we do Leibniz notation, it's going to be, remember this L goes on top, right? And then we're going to have D over D, right? That's just Leibniz notation. And then whatever it's a function of, the Q goes on the bottom. And then to write this, so then to say this same thing, f prime of 10, you would have to say when Q is equal to 10, like that. And then it ends up equaling 0.5. And of course, this is hours per milligram. All right, so what's this mean? What are the units? What is, oh, C should be here. Yeah, here we go. Okay, so what's this mean? Let's remember what this is. This is, let's remember what, let's see. So if we say, here's the prime way. Oops, I'm on the wrong problem, sorry. So this right here is your quantity. Or you could call this a dose. And this is the derivative, which is the instantaneous rate of change, right? And it tells you what will happen if there's one unit. Like, for example, if you go from f prime of 10 to f prime of 11, 1 unit, then that's what you can expect the rate of change to be. So we can say at a dose of blank, the rate of change, I should say instant, in time is blank hours. So what do you guys think? And we'll get it, we'll make it finer. What's the blanks? A dose of what?
10.
Yep. Dose of 10. The rate of change in time is 0.5 hours, right? Okay, well, let's get this down. So remember, derivative is, what if we make a unit change of 1 unit, right? So we can further delineate by saying, if we increase the dose by 1 milligram, then the drug stays in the body um, 0.5 hours, which, by the way, is 30 minutes, right? 30 minutes longer. Thirty is positive, right? So it's increasing. All right. See you guys writing. I'll bring this down. Where'd all my people go? Grady, Tom, Joey, Dylan, James, Sean, Will, Connor. There you guys are. I can't tell you what a great difference it is for me to see faces. You know, my day job with the high school where I teach, they don't have to show their faces, and it's just awful. So it's really nice that you guys do that. I appreciate it. It's nice to see people's expressions, you know, when they're like, oh, I get it, or well, it doesn't make sense to me, right? It just makes it easier for me as a teacher. So thank you. All right. So here's a new topic. This is relative rate of change. We haven't done this yet, okay? We have done relative change, but not relative rate of change. So basically what this is saying here is, this is Leibniz notation, right? dy over dt over y. So really what this is saying is that you can find the relative rate of change of y at f of t at a certain value of a. You can find that. All you're doing is taking the derivative at a and dividing it by the function at a. So all that notation is just saying, take whatever the derivative is and divide that by whatever the function is at that same value of a. Okay, so let's do some color coding here. All right, so annual world soybean production is W is a function of T, where T is in years, since the start of 2000. That's always important, right? Interpret the statements. F of 8 is equal to 253. So that would be this blank and this blank. So what do you guys think? Now remember, this is T years since 2000. So produced in, that suggests that we're talking about a time. So produced in what year? If it's years since 2000.
2008.
Yeah. Okay. And then remember, W is the soybean productions in million tons, right? So you would say that 253 million tons of soybeans were produced in 2008. Okay, now let's move on to the derivative term here. So here, f prime of 8 equals 17. This says that in what year? I remember,
Still 2008.
yeah, 2000, still 2008. Yes, thank you for saying that still, Tom. You're absolutely right. Because by definition, we've got the derivative at A divided by the function at A, right? So the year's not going to change, right? We're evaluating the derivative as well as the original function at that same value of A. This time it is 2008. So we can say in that same year of 2008, the soybean production was increasing or decreasing?
Increasing.
Yeah, and why do you say increasing, Kevin?
Well, I was just looking at like f of 8 equals 253 and f prime of 8 equals 17. So they're both positive numbers.
Well, you're exactly right. This means increasing, right? It really, the fact that the rate, remember, derivative is the rate, right? The rate is a positive 17, right? So that means increasing. If that was a negative, then you would say decreasing. By how much?
17 million.
Yeah. Per what?
Is it per year?
It is per year, yeah. All right, good. I think you guys are getting like the difference between here. Okay, so now we're going to calculate the relative rate of change of W at T is equal to 8. So we're going to do F prime of 8 divided by F of 8. Well, we know what F prime of 8 is, right? What is it?
Is it 17?
It is, right? It's 17. And then F of 8 is what?
253.
Yeah, good. Trying to find a different color here. There we go. So if you put that in, you get 0.067. All right, so let's interpret what we're saying here. In what year? What year is the annual soybean production was something?
2008.
Yeah, we're still in 2008. Very good. So, oops. In 2008, the annual soybean production was increasing or decreasing?
Increasing.
Yeah, increasing, right? Because remember of this positive 17? At a continuous rate of, what do you think the rate is? So we just got the rate, right? So this would be as a percentage, 6.7%. Per what again? What's the unit of measure? 6.7% per,
Year.
yeah, year. Okay, so they could give it to you like this by giving you basically two ordered pairs, right? And you know that they gave you what F prime of 8 is, and you just plug it in yourself. Or they could give you a problem that looks something like this. So solar photo voltaic PV cells are the world's fastest growing energy source. At time T in years since 2010, that's important, right? That's something that you could circle. Peak PV energy generating capacity worldwide was approximately equal to that equation in gigawatts. estimate the relative rate of change of PV energy generating capacity in 2018 using this model with change in T is 0.01. So we'll start like we did before, right? We've got F prime of 8, right? We're talking about 8 years difference. F prime of 8, I should have picked a different number, not 8 again. It's not always 8, right? All over F of 8. So I'm going to write this slightly differently so that you guys can figure it out easily. So you can write this as 1 over F of 8 times F prime of 8 over 1. So we could say that's equal to, all right, I'm going to just leave this alone, F of 8 times, now I'm just going to use the formula itself, right? So I'm going to do F of 8.01 minus F of 8. That's where this change in T comes in, right? All over 8.01 minus 8. Well, what does that mean, F of 8.01? How do I find F of 8.01? What do you guys think? If I gave you that equation and said find F of 8.01, what does that mean? You're going to put that in for your variable, right? So F of 8.01, well, first let's do this. Let's do this in a different color here. So F of 8 is equal to 50.15 E to the 0.32 times 8. And if you put that in your calculator, you would get 648.73. If I said, all right, well, what's F of 8.01? Well, that's the same thing as 50.15 E 0.32 to the 8.01. If you put that in your calculator, you're going to get 650, legible, 0.81. So now all you have to do is put it in your calculator. So F of, let's finish over here. Let me erase this though. So F of 801 is 650.81. Minus F of 8, which is 648.73. Divided by, we would just do 801 minus 0.8, which is 0.01. Oh, and I forgot 1 over F of 8. So let's see, we'd get 1 over F of 8 is 648. I'll put this in a color. We know it's 648.73 times this would be 2.08 over 0.01. Put that all in your calculator and you get 3.3206 or 32.1%. And that would be your relative rate of change. Anybody have any questions?
Yes, I have a question. If you can just go over where you got 2.08 from again.
I just took 650.81 and subtracted 648.73.
Oh, okay, never mind.
That's fine, and I'm sure other people had that same question. All right, we have a few minutes left. I want to do one other extra example because I was looking through the Wiley problems and I want to make sure we're clear on this. So let's say you had a function f of x. Let's say f of 15 is say. Let's say f of 15 equals 73 and f prime of 15, same year, is equal to -4. And I wanted you to estimate f of, estimate following. Let's say f of 16. Well, since they're giving you the derivative for every increase of 1, you know, like if it went from 15 to 16, it's going to decrease by 4, right? So we know that f of 15 is 73, so f of 16 must be 73 minus 4, because 16 is 1 more than 15. So that will be 69. Now, if I said, what about f of 14? So it's going to decrease by 4, but if we're going backwards in time, it's actually going to be increasing, right? So it would be 73 plus 4, because it's got to subtract 4 every time, right? So that will give you 77. And if I did like f of 19, well, 19 is 4 more than 15, right? So we're going to do 73 minus 4, the rate of -4, rate of 4 times. So here you're going to get 57. So this one is 1 above, right? So you just subtract 1 rate of 4. This one would be 1 below. So you're going to add a rate, 1 rate of 4. Really, we could say something like 1 in here and here, right? Because it's just 1 unit away. But 19 is 4 units away. So that would mean that you could predict that f of 19 would be 57. All right, and that's it. You should be well armed to do your homework. And it's not a tremendous amount either this time. So let's see, do we know the due date? Let's see, today is, what's this? So you have homework 2.3 to 2.5. It's not due until March 7th. So you might be able to finish 2.3 quickly while it's still fresh in your head. So I think I would go ahead and start that. It looks like it's not even posted yet, though. I'm gonna do that right now. Post the homework. Okay, so I will post the video since we're not cutting out on internet anymore. We shouldn't have any more issues with that. As you notice, I'm in my kitchen now where my router is. That's all I have for you. Does anybody have any other questions for me?
Just go back to the first page for me because I like didn't write something down.
Yeah, sure. So the rest of you, if you don't have a question, you're free to go. But if you have a question, you can stay too.
Have a good day, Professor.
All right.
Thank you.
And Philippe, you're gonna stay, right? Oh, he left. No, he's here. Good, good.
I have a question.
Yeah, yeah.
Go ahead, Jadelle.
When you're done with this page, do you mind going back to example 4, the relative rate of change?
No problem at all.
Thank you.
Uh-huh. So let's see, Philippe, are you available tomorrow? Are you ready tomorrow?
Thank you.
So I was gonna request if I can maybe take it on Thursday,
All right.
just because everything is like so jam packed together.
Yeah. No, I don't want to rush you. I'm glad you're looking better.
Yeah, thank you. Yeah.
Let's see, Thursday. Yeah. Do you have any time during the day? Like, I'm
Absolutely. Yeah.
trying to get you to do it while I'm already teaching my other classes, so I can have two things going on at once. So
hmm
I on Thursday at 12 o'clock. Could you do that?
Thursday at 12 o'clock. Yeah, that works.
All right,
Yeah.
great.
Perfect.
So what I'll do is I'll send
And
you. Go ahead.
I was just wondering if the previous class, if you've already posted that recording on YouTube, because I think I missed it.
I know that the 22nd is messed up, but you mean that our last class?
Yeah, like the most recent class. Yeah.
I'll make a note to do that.
Okay. Because I missed it, so I'm not ready for the homework.
Yeah, okay. All right, so you're gonna take the test 12 noon, so I'll just shoot you a copy of it right when we get together. It's not gonna be the same as everybody else's, but yeah.
And would it be online, or would it be
No, I'm gonna
at
send you,
school?
I'm gonna send you basically a Word document.
Oh, okay.
Do you have a
So
printer?
I'll just scan it to you?
Yeah, do you have a printer?
Yeah, I could just scan it to you. Yeah, I do. Mhm.
Okay, perfect. That works it out even better.
Yeah.
All right, cool.
Yeah, I
So-
could just scan it to you. Yeah.
Okay.
All right, perfect. Well, thank you.
You're welcome. I'll see
All
you Thursday.
And what
Oh,
did you would
and I'll see you
you would send it on Thursday?
Yeah,
Okay.
right before you take it, and then give you time to
All right.
print it out, obviously.
Got it. All right. Thank you.
You're welcome. I'll see you then.
Bye-bye.
Alrighty, so it's example 4. I just want to know, I think, did you multiply both the 2 point, the,
Sorry, let me go to example 4.
okay. Yeah, so you see how there's like, obviously you can't see my screen, my mouse, it's at the bottom.
Wait, I wonder if I can move this whole thing down. Yeah, I can. Let me do that. Okay, go ahead.
Alrighty, so it's 1/648.73. Is that number being multiplied by the 2.08 over 0.01? Is that how you got the 0.3206?
Yeah, I'm taking 1 and multiplying it by that.
Okay,
And then I'm taking this and multiplying it by that. And so I'm dividing this by
Right.
this times this.
okay. Alrighty, thank you. I was just confused.
Yeah, no.
Because when I did it, I didn't get the right thing, but okay.
Well, let's see. Let me do it myself.
Oh,
Before
no,
we-
I didn't multiply the 1/6. Like, I didn't have that part. I thought that was just like another part of the problem.
Oh, okay, I got you. All right.
Yeah, alrighty, thank you.
You're welcome. Have a good night.
You too.
Thanks. Bye.